So what is proxy re-encryption? Well, the basic is that you take a ciphertext encrypted to Alice, you send it to a proxy, and that proxy transforms it into a ciphertext encrypted to Bob. And it does all this without ever getting any information about the encrypted message or the private keys of the other parties, meaning it transforms from ciphertext to ciphertext without decrypting in the middle. Proxy re-encryption was first proposed by Matt Blaze and Garrett Blaumer and Martin Strauss in 1998. It's been an active area of research, and there's thousands of papers on the subject, hundreds of schemes. It's a very broad category, and there's lots of different nuances to different approaches. But one thing I'll note is that re-encryption is unintuitive as a name, because typically when we talk about re-encrypting something, we mean we're going to decrypt it and encrypt it again with a new key. In re-encryption, of course, proxy re-encryption, we don't decrypt it. That's why we call what we do here at Iron Core Labs Transform Cryptography instead. And we do that and we apply it specifically to a set of properties that we think matter a great deal in a proxy re-encryption scheme. One of them is unidirectional. That means if Alice encrypts or delegates access to Bob, then it doesn't imply the opposite. Multi-hop, meaning Alice can delegate to Bob, who can delegate to Charlie. Collusion safe, meaning that if two participants get together, they can't find the key of the other participant. Non-interactive, non-transitive, and CCA2 are a few other properties that we think are pretty important. In our incarnation of how we do proxy re-encryption, we focus on groups. Basically, in a classic re-encryption scheme, what happens is Alice encrypts to Bob and Bob delegates to Charlie. It's usually used in this case of like, hey, I want someone else to be able to read my emails. At least that's the use case that's most typically talked about. What we do is we stand up a level of indirection and we call it a group. So we can encrypt to a group, Alice can encrypt to a group, and the group owner, whoever that may be, can add, for example, Bob and Charlie as members, or another group as a member for that matter. And that way you can encrypt the file once and then you can change who can access it later without touching the file again. We call that property, by the way, orthogonal access control. So here's what it looks like. Basically, if you have plain text, we're talking about elliptic curve cryptography. So these are standard elliptic curve key pairs. You take the plain text, you encrypt it to the group's public key, and that's it. You have some encrypted data encrypted to a group. And then in theory, the way this works is that a member of the group can use their private key to decrypt that data. But there's actually one step missing here, and that is that transform step that's done by that semi-trusted proxy. So the data that's encrypted to the group then requires a transform key that goes specifically from that group to the member, to that user. And then there's this transformation that happens that makes it so that now effectively the data is encrypted to the user, and now the user actually can use their private key to decrypt it. So looking at this kind of zoomed out a little bit, a group has a key pair, every member of the group has a key pair, and the relationship between each group and the member of each group is basically what we call a transform key for each member. So if that transform key exists, they're a member of the group, and if it doesn't, they aren't. And those transform keys, by the way, are held by that semi-trusted proxy. That's to preserve the revocation case. If the member held that transform key, you could never take away their access. So the way a transform key is created is basically it brings together. This is specific to what Iron Core is doing here, not to the general practice of proxy re-encryption. Okay, so different proxy re-encryption schemes do this differently. In our case, it requires the group private key, which the administrator of the group has access to, and the public key of the person they want to add as a member. Those two things come together to make the transform key, which is stored with Iron Core, but it does not leak any data except for that membership information. And I mentioned earlier, of course, you can nest groups. In practice, the way we do this is by modeling a member of a group, a user, as actually a collection of devices, a group of devices. So in fact, what happens is a user can add and remove devices if one were to be lost or stolen, or they get a new one or something. Each one has their own public-private key pair. It's generated locally. The private key for the device never leaves the device. And in fact, in our system, only device keys are able to decrypt data. User keys and group keys can't directly decrypt data, not without some kind of transformation happening first. So in this case, this is effectively a group of a group that you're looking at here. And the implication is that if you remove a member of the group, you're also effectively removing all of that person's devices from having access to the data. Why does this matter? It matters because in the general case of how we control access to data, we basically put access control checks in at the application layer or some data layer or API layer that does that. The trouble is, of course, anyone with access to the database, maybe a database administrator, maybe someone who works for Amazon Web Services, if that's where your stuff is hosted, or a developer or a hacker, all these people can bypass that access control check and get direct access to that data in the database. So in the classic scheme of how we do things, we really hope all the access goes to the access control layer. We hope no one writes code that bypasses it. We hope no one kind of works around it. When you encrypt the data, frankly, whether you encrypt it using Proxy Re-encryption or another scheme, you move the access control to the data such that it doesn't now matter who has access to the database. What matters is who has access to the keys or who is able to decrypt it. So you can know that the access is controlled if you do that right. With us, the access control stays with the data wherever it lives. So even if it moves out of that database, as long as it wasn't decrypted before it was copied out, the data is controlled and you can know who has access to it. The last thing I'll say on this is that there's actually other schemes here. The Proxy Re-encryption, the Transform Cryptography, makes it pretty easy to develop end-to-end encryption schemes with zero trust properties, or really semi-trust, if we're talking about the fact that the metadata is held by and the revocation is a trusted thing that the server does. We also support a number of other schemes, not all of which use Proxy Re-encryption, including customer managed keys, server-side encryption, decryption, and trust but verify schemes where any access is at least logged and is revocable. So those are some of the things we do, and we're Ironcore Labs, the data privacy platform for leveling up your data control in your application. Thanks.